rotate that region around a whole bunch of different things. But first, let's just think about what that region looks like. So we can do this with a picture or without a picture, but when I'm doing volume, for me, it really helps to have a picture. So I want to start by saying, I know this is some kind of parabola. The number in front of the x squared is positive. So I know that this is a concave up parabola. This is some kind of line with a negative slope. So if I were drawing a fake picture of this, I'd have something that looked like a concave up parabola and a line with a negative slope. So before we can talk about anything, we really need to figure out where those intersection points are. I'm going to set these two equations equal to each other to find those intersections, and then we can get a better graph going. If x squared plus 3x is equal to 5 minus x, we have a choice, but I want to get everything on one side of the equation, so I have a 0 and I can factor. I'm going to add x to both sides so that I've got x squared plus 4x, and then subtract that 5 over. And if I've done this right, it's going to factor for us. I think that's going to look like x plus 5 times x minus 1. So I know I've got two intersections. One of those is happening at x equals negative 5, and the other one here is happening at x equals 1. So if I draw this a little bit better, I know that this parabola, I could factor an x out. So that's the same as x times x plus 3, which means that parabola is going to have x intercepts here at 0 and at negative 3. And I just realized if our intersection points are negative 5 and 1, I probably want a little more space on the left-hand side of my axis. So let me get this going over here. So I know we're going to intersect at 1 and negative 5, and I know for our parabola, we're going through negative 3 and 0. And now I know, since our intersection points are at negative 5 and 1, I'm just going to draw my line in from there to there. So that's my y equals 5 minus x line. So here's the region we're looking at. And if I need to spin this, let's say that I'm taking this and I want to find the volume. If I take this shape and instead of spinning it around an axis, let's have fun and spin this whole thing around the line. Y equals negative 4. Negative 4. Good times. Well, in general, in the context of 17b, and I mentioned that at least in our textbook, we do not discuss the shell method. So if you know that from a previous life, that's not a method that we talk about in this class. So if I'm going to revolve around y equals negative 4, the first thing that I want to do is to think about what does an arbitrary cross-section look like in this region. So I kind of squiggled that in, but let's actually draw a rectangle in for ourselves. To draw in that arbitrary cross-section. So that when I spin this around y equals negative 4, I know that the shape that we get is going to have this hollowed out part in the middle. It won't be solid. So when we go to find our volume, we're going to need to use that volume equation. It's like a big volume minus a little volume, or a pi big R squared times dx minus a pi little r squared dx. And both of those I know we're going from negative 5 to 1 because those were our intersection points. And then if we think about the big radius, little radius, I'm going to start at my axis of rotation, or what I'm spinning around. So here I'm spinning around y equals -4. And to find that big radius, I've got to go from that axis of rotation all the way up to my function. Now, I made this one a little bit messy, but in terms of that y function, if I'm standing right here, that line tells me the y value, but that's really giving me this part of the height. In terms of that entire outer radius, that distance from y equals -4 up to the axis is a 4, which means that outer radius is really going to be 4 plus the equation of the line. So I would be looking at something like pi, -5 to 1, and I'd have 4 plus the equation of the line, 5 minus x, whole thing squared, minus, and now we're going to get our inside function. And that inside function, my radius would go from the axis of rotation up to this closest edge of my arbitrary cross section. So I've still got the 4 and then plus the y value from the parabola. So I'd have 4 plus x squared plus 3x whole thing squared dx. Given time, energy, and sufficient monetary motivation, I'm guessing folks could finish this off. Now, I do want to address specifically question 2. While we're not going to work entirely through the problem, we can at least talk about what the picture looks like and the volume in question. And then I know somebody else wanted to talk about number 3. Again, we can do the same kind of thing. We can talk about what the picture looks like and then sort of generally. Now, the question in the chat about how I got this to be 4 plus 5 minus x. So the y value for the line, and I'll got kind of messy over there. Let me come over here. So if I think about when x equals 1, the y value for this line is 5 minus 1 would be 4. So this right here, that intersection point is the point 1, 4. So that 4 is the y value. But if this line down here is y equals -4, okay, not drawn to scale. But if this value down here is y equals -4, then the distance from my axis of rotation up to that point, the distance from y equals -4 up to 0 is a distance of 4. And then I'd have to go 4 more to get to that intersection point. So that radius is the distance from the axis of rotation to our arbitrary cross section. And in this case, that means we've got to go 4 plus the y value. So for that outer radius, that's 4 plus the y value of the line. And for the inner radius, that's 4 plus the y value of the parabola. Now, we've done this problem before. I know that's the 0.28. This is the piece I want to look at. Question, should we try to email him about number 2 before the homework is due today? I don't know what to do. I don't have a great answer. My recommendation is someone should email him right now. But really, it would have been great if it hadn't been left till the last minute. However, better to email him now than never. I was just kind of surprised that that it hadn't like shown up on Piazza before this. Anyway, back to here. I'm going to find the volume of this if I revolve it around the y-axis. So in the context of 17b, when I'm drawing that arbitrary cross section or my rectangle, I need to draw my rectangle perpendicular to the axis of rotation. Since this is my axis of rotation, that means I need my cross section to be horizontal. That same kind of idea is going to apply when I spin this around in a circle. I'm still going to get pi times a radius squared times a little bit of thickness. The difference here is that my little bit of thickness on that rectangle is a little bit of dy. So I'm going to have something squared and a little bit of dy. Since I know that I'm going to need a little bit of dy, that means that I'm integrating this entire thing with respect to y. There should be y's in here. Since there should be y's in here, when I go to write my radius, and I'm thinking about the distance from the y-axis out to the edge of my arbitrary cross-section, I know that it's hitting this curve, but I'm going to have to rewrite the equation for this curve to make it say x equals y to the 1/3 power, because what goes in here has to be something that matches that dy. So it's got to be y to the 1/3 power. Also, because it's a dy, I know that means that when we write our limits of integration, those limits of integration need to match the y values. So they're going to come down as far as y equals 0 and up as far as y equals 8. So this is going to be going from 0 to 8. Phrases. So growth rate, and then the per capita growth rate. So when we talk about growth rate, we want to think rates of change, 17a, that means we're taking somebody's derivative. Usually if we're talking about the growth rate, we're talking about the growth of a population. And our book has chosen n, and I think that's pretty standard, to represent the number of individuals in a population. So that phrase growth rate, really we want to read that as dn dt. Now, when we talk about per capita growth rate, that per capita, per usually means we're dividing by something. Capita means the population. So the per capita growth rate says I'm taking the growth rate, the dn dt, but dividing that by the number of individuals in the population. Or sometimes we'll write that as 1/n times dn dt. What the logistic growth model says specifically is that the per capita growth rate varies linearly from a value of r when n equals 0 to a value of k, to a value of 0 when n equals k. So I said that out loud, but let me actually write that down. So when we talk about logistic growth, then we see that the per capita growth rate, is linear, meaning we're going to write the equation of a line. So the per capita growth rate is linear from a value of r when n equals 0 to a value of 0 when n equals k. Well, that's a bunch of words, but since we're talking about something linear, let's think about that graphically. So rather than labeling these axes the way that we might normally think about labeling them, as like an n or a population value and time, what this relationship is telling us is that the per capita growth rate is what is acting linearly. So my per capita growth rate of dn dt is doing something depending on the value of my population. So when my population starts out at 0, okay, really if my population is 0, you have no animals, they can make no babies. So we're never really at 0. But if n were really, really, really close to 0, then the per capita growth rate would be equal to r. So here's my per capita growth rate of r. Now when we get to some point where my population has reached a value of k, and we usually talk about k as the carrying capacity, when I've reached a value of n equals k, then the per capita growth rate shrinks to 0. Meaning when we've hit that carrying capacity, the growth rate of my population stops. My population stops growing. So our logistic model comes from thinking about this particular linear relationship. Well, we know how to find the equation of a line. So if I write the equation of that line, here's my y value. And if I think about this as like an mx plus b kind of thing in terms of the equation of the line, that b is my y-intercept, which in this case is r. We're not really talking about an x value because all of this is relative to the size of my population, or n. And in terms of that slope, well, just from looking at the graph, if I think about rise over run, we've gone down r and over k. So I'd have negative r over k. And this relationship right here defines logistic growth. But that's not usually the way we're used to seeing it. We usually rearrange this equation. So if I take that equation and I say, well, I don't really want to have this 1 over n over here. I actually just want this to say dn dt. Then I can multiply both sides by n. And here, I'm going to rewrite that to look like negative r times n over k plus r. And then do 2 more math tricks. One of those math tricks is to factor an r out, so that I've got dn dt equals r times n. And my last math trick is to say, mathematicians don't always like there to be a negative number in the front, but if I switched the order of these, it would look like 1 minus n over k. And this right here is one of our classic forms that we write that logistic growth equation in.